All right, so hopefully you'll be able to hear me this time. If not, I will try this again. But anyway, I'm going to dive back into once again talking about our last couple sections of complex experimental designs. I think I'm going to break it up into videos 4 and 5 this time instead of just one big long fourth one. For a couple of reasons, mainly so I can see if I've made an audio mistake again. But where I left off last time, I was talking about that Bazzini and Schaefer study about romantic interest in a hypothetical stranger, and talking about the different ways we can look at an interaction. And I'd been introducing this idea that you can just sort of look at mean differences across different cells, but there are other ways we should look at interactions too, right? We should be able to look at them graphically in figures, and we should be able to look at them with statistical methods like ANOVA, we'll talk about today, but you could also do other methods like regression, for example, to see how the combined effects of different independent variables influence a dependent variable. So just to talk real briefly again about the way you can look at the means. Remember this kind of 2 by 2 that we've been working with of dating status crossed with type of scenario. And if you wanted to look, for example, at whether dating status makes a difference within these scenarios, if you look at stranger attracted to friend and look at the difference between dating statuses, there's not really much going on there, right? It's less than 1/4 of a point on the scale, not that big of a change. But if you look at when the stranger is attracted to the participant, then dating status makes a pretty big difference. Non-exclusive daters are much more likely to have romantic interest in that hypothetical stranger than people that are in a committed relationship. There's a difference of almost 2 points on that scale. So there seems to be some kind of interaction. The type of scenario is influencing the size of the effect of dating status. In one condition of type of scenario, dating status doesn't matter. But in another type of scenario, dating status matters a lot. So this is one relatively simple instance of an interaction. But again, it's kind of hard to interpret exactly what these things mean just by looking at the numbers. So it's really helpful to have multiple ways of looking at interactions. Obviously, I've mentioned them already, looking at figures and actually testing them statistically. But even by looking at those figures, you can tell there's not really much of a difference for the stranger being attracted to a friend, which makes sense, right? That you're going to maybe just have some kind of middling level of attraction or interest to this person when they don't seem all that relevant to you. But when they become relevant to you because they're attracted to you, the participant, then that's where we see some effects bearing out. So like I mentioned on that last slide, that small difference isn't significant, that bigger difference is significant. So how else could we look at this, though? We could look at this by using a method that many of you are at least partway familiar with at this point, by using ANOVA, or analysis of variance. It requires a little bit different of an ANOVA than we've used previously, though. A two-way ANOVA is an ANOVA that uses that uses 2 independent variables. The ANOVAs that you used, if you used one for your studies, were one-way ANOVAs because you were just predicting differences along one independent variable. To do a two-way ANOVA with an interaction, you test the main effects for both of those independent variables and you test their interaction. And if you were to run this type of ANOVA on that study, this is the type of output you would get. You'd have a row for your first independent variable type of scenario, you'd have a row for your second independent variable, in this case dating status, and you'd have a row for an interaction. Now, you'll notice this interaction is typed out as type of scenario times dating status, or frequently people will say a type of scenario by dating status interaction. Both are, kind of reasonable ways to phrase this. But it's also useful to know that this multiplication sign, or if you phrase it as times between those two variables, that is a very literal thing. So the way that you come up with these terms for interactions actually is by multiplying the values for your independent variables together. So for each participant, Let's say they had a 0 in the dating status column and a 0 in the type of scenario column and a 1 in the dating status column. Well, you'd multiply that out, and so this person would have a 0 in this column here. So your interactions are very literally the products of the independent variables for each participant, and that is how, when you have all three of these things in an equation, the ANOVA math spits out what it's like when those variables combine with one another, basically. One other important thing about looking at this type of output is that if you just had type of scenario and dating status in this ANOVA without the interaction term, then you would look at these as real tests of the effects you're interested in. You'd be able to see, does dating status matter, does scenario matter? However, when you have higher order terms or interaction terms that are multiplying those other things together, once you enter these things into an ANOVA, these estimates up here become unreliable. So if you have interactions in a model, you really shouldn't interpret the lower order or main effects. So if you ran this ANOVA, you'd obviously be focused then on type of scenario by dating status interactions. And you notice here your F statistic relatively high, it's at a 5, and the p-value is below 0.05. So this would give you some indication that there is some sort of meaningful interaction. But if you just look at these numbers, it's hard to really interpret exactly what that means. So when does the level of one variable depend on another? It doesn't really tell you anything explicitly about what matters and what doesn't. To actually figure out what an interaction is like, you need to do some follow-up things, like looking at figures and doing post hoc tests or contrast, or looking at simple effects, for example. The most straightforward thing, I think, is looking graphically at your data. And when you're doing this with line graphs, you kind of have an easy rule of thumb that if your lines are going to cross, or they have crossed, or they look like they would eventually, that tells you something that there's probably an interaction going on. So what I mean is this. This is the data from that Bazzini and Schaefer study. What it looks like is, sometimes people say it looks like an alligator mouth or a Pac-Man or something like that. But it might look like a V on its side, or an X if these things crossed all the way. But if you have anything that is crossing or looks like it's going to cross, that's a pretty good indication that there's an interaction going on. If you had parallel lines, then that would indicate that there was not an interaction, because the differences within conditions for a particular variable don't depend on another variable, basically. But with this one, you can tell the effective dating status in the friend condition. There's not really any difference between the two different types of dating statuses here. The difference of dating status in the participant condition is pretty big. So the way that you want to make sure you're interpreting these things is by remembering that one of your independent variables is on the x-axis, one condition here, and your other independent variable is plotted as different points on a line. So dotted line being non-exclusive daters, solid line being exclusive daters. And then the higher you go on the y-axis, the higher your return, or the higher your outcome on your dependent variable is. So this one would indicate an interaction. But you can't really just look at a figure and eyeball it and say, yes, there's an interaction. I mean, it seems pretty obvious, but you need to really pair that observation with output like this to know for sure what it is, and then being able to give yourself an idea of what it actually looks like. Okay, so altogether, what does all this stuff actually mean? Where are the effects that really matter? And when you get a significant interaction, you then have to figure out where the actual meaningful differences are, right? So if you didn't have an interaction, if you found there was no significant interaction, like I mentioned earlier, if you had parallel lines or something, this would give you an indication that you need to pay attention to your main effects. So let's say we had condition a variable A, B1, B2, and B3. You see here on this panel for the no interaction side. So on your B variable, you have 3 conditions. Well, I guess these might be 3 time periods. So maybe we should think about this as a well, I'm not going to make up an example for this at this moment, but if you notice that these lines are basically just tracking each other and they're parallel, there doesn't seem to be any kind of interaction. It's just that one variable is always higher than the other. So maybe there's a main effect of the red condition being higher than the blue condition, for example. For these, there does seem to be some kind of interaction. These things are crossing. And if you really just looked at the averages in the blue and the red condition, right, they probably both are somewhere in here. So the main effects wouldn't really tell you anything, even though there's some interesting story here about why the red condition gets higher over time or across these conditions, and the blue condition gets lower over time or across these conditions. So if you do find an interaction, generally you don't talk much about the main effects because the interaction, again, statistically kind of subsumes those things, and the interaction is usually the more interesting or complex story that you're able to tell. So instead of looking at the main effects, you look at what people call the simple effects or the simple main effects. I think the term simple main effects is a little confusing, so to distinguish it a little bit more from main effects, I tend to call it simple effects, so that's the terminology I'm going to use here. But this is just looking at mean differences at each different level of independent variable. So looking at each different cell in that 2x2 or whatever your design happens to be, to compare them to each other and tell where the differences actually are. So in the Bazzini and Schaefer example, we have 4 possible effects here. And I have this on the 2x2 design on the next page so you can kind of tell what I'm talking about, and they're numbered the same way. But the simple effects, what I mean by these are within each condition, for one variable, you can talk about the differences in another variable. So within the stranger attracted to friend condition, there's an effect of dating status. Within the stranger attracted to self condition, there's also an effect of dating status. And vice versa, in the exclusive daters condition, scenario has some kind of effect, and within the non-exclusive daters condition, scenario again has a type of effect. So these 4 different comparisons, you can represent them as maybe arrows or lines on that 2x2 space. That the effect of dating status for all of the people in the stranger attracted to friend condition is this comparison here, number 1. The effect of dating status for people in the stranger attracted to participant condition is represented here with the second line, comparing these 2 boxes. But then you can also look at the effect of scenario in the different dating status conditions. So for exclusive daters, scenario is represented here with this 3rd line. And for non-exclusive daters, the effect of scenario is represented here. So you need to look at all these comparisons, these simple effects, to see where the interaction is actually, having some kind of action, basically. And if we look back at our figure, it might be a little easier to think about exactly how these things are represented. So, 1 second here. So your first simple effect, dating status for people in the stranger attracted to friend condition. You see, these are all people in the stranger attracted to friend condition here. And you can compare people on the dotted line to the solid line of non-exclusive versus exclusive daters. So no difference here, right? These are very similar values, not much of a change. The other one where we see more action, the participant attracted to participant condition, you see a pretty big difference going on here. And you can tell that these things are, significantly different. If you run a test, then you actually would find that these are very, very different. But then it leaves the question open, does, type of scenario matter within these different conditions? And if you test both of these things, there's kind of a trend here, but they don't actually turn out to be statistically significant from one another. So, there's some kind of trend. Maybe if at a bigger sample size and at a smaller measurement area, these things would be significant differences, but they don't actually tend to be in this particular sample. So Bazzini and Schaefer, when they put this together, they found that romantic interest depends on the dating status of an individual and whom the potential dating partner is interested in. It's not just that one of these main effects mattered, it's that they interacted with one another to tell a bit more of a complex story. I'm going to end this video here and talk a little bit more about how to think about figures in graphical interpretation, and we'll wrap up this topic.